Hello and welcome to another video lesson with Lawson. We're going to be looking at the elements related to descriptions of motion by describing the variables and concepts that we need in order to be able to describe the motion in the universe. One of the first things that we have to use to be able to describe motion is the concept of time. The idea that when motion takes place, time also elapses or goes by. Different reference points for time. We have an initial time, a point when we start observing an object or when we start noticing a phenomenon. We have a time at which we are observing the phenomenon later from when it started. Often the initial time will be 0. That's nice and easy when you have a stopwatch. If you're looking at an actual clock, the initial time is not 0. The initial time might be 1:30 in the afternoon or 2:30 in the afternoon. That would still be our 0 time at that point, so we could make that as 0 and then reference time as it passes from then, or we could keep it as 1:30 or 2:30 or whatever the time might be. There's initial time and then there's a time at some point later. We'll refer to the time at some point later as the final time or the time at the end of the observation, but we might be observing something that takes place over a long period of time, and we might be looking at increments of time in between the beginning and the end of that observation, and we'd still refer to those just as t. We use t naught to represent the initial time, or t sub 0 to be able to represent the initial time. When time has elapsed, the amount of time that has gone by, or what we'll refer to as the change in time. It's pretty straightforward. The change in time is the difference between the time when we started observing it, or t naught, and the time that we're at that instant in time. So we simply take the instant in time and subtract from that t naught, or that initial time, and we get the amount of time that has elapsed, or the change in time. In addition to be able to refer to the time when we're observing an object, we also want to be able to describe the position when we're observing an object. It's expected that you're already familiar with coordinate systems, and you already have some kind of idea of what it means to describe the position of an object in space. In this case, what we're looking at is that spatial description of where it's located. The most common coordinate systems that we'll use are Cartesian coordinate systems when we describe something as an XYZ plane, or polar coordinate systems when we describe something in terms of its length and then angle. There's several different coordinate systems that can be used, but those are the two that will be common and that we'll often refer to. Identify your coordinate system, or you identify your frame of reference so that we can use that when we're describing the motion carefully. In terms of your position, where that is relative to the origin is arbitrary, because we could make that position the origin, or we can make a different position the origin. The initial position is actually not as important as the origin, or as where that initial position is relative to. As we see here in this diagram, we had that initial position, but now we have that position on a map, and now we have it relative to streets, we have it relative to corners, we have it relative to other locations identified as other dots. It's important that we not only identify the coordinate system, but that we also identify at minimum the origin relative to that if it's not the origin itself. And if it is the origin, we also need to be clear that we're deciding that the initial position is the origin on our coordinate system. Kind of like time, there's your initial time when we start, and then there's your final time. There's your initial position, and then there's your final position. If you're not moving, if you haven't changed position, then it's very boring because they're both the same. However, when we have objects that are undergoing motion or are changing position in the universe, then it becomes interesting how we understand or describe where we started and where we end, and what happened in between those 2 points in space. Similar to the change in time, we will want to be able to get the change in position. And we'll get the change in position the most direct, or what we'll refer to as the displacement between the initial and final, without regard to what happened in between those 2 points, by subtracting the initial position from the final position. To start tying into some of the calculus that we were introduced to, one of the concepts that's going to be important when we're describing motion is being able to recognize how different variables that describe motion are related to each other in terms of derivatives and integrals. The change in position, or the displacement of the object, is the integral of the velocity in terms of time between the initial time and final time. If we have a function that describes the velocity, we can apply the integral rules, and that integral function will end up giving us the change in position. We'll also want to be able to describe the velocity of an object. When we describe the velocity of an object, the velocity is the derivative of the position in terms of time. So if we have a position function, we can take the derivative of that function and we'd have the velocity function that would describe the velocity at every instant in time. What we also want to be able to do is, again, like we were describing with position and time, have an initial velocity and a final velocity. When we are speeding up or slowing down, when we're changing direction, then our velocity is not constant. We have to be able to reference those different points. If you have a constant velocity or velocity that's not changing, then there is no initial or final velocity because the velocity is the same at every point along the motion. In this instance, we noticed a car driving in from the left side, and it actually hasn't stopped, but we've paused time to be able to describe its motion. If we didn't pause time, the car would have just continued going in a straight line. We paused it so that we could start describing or start looking at the motion of this car a little bit more clearly. We already can make some predictions since we happen to know what it was doing before we were looking at it. Imagine we didn't. This instant in time, there's no way of knowing whether it's moving or not moving without other information. We unpause time and we notice that the car continues on to the right side of the screen at what appears to be a constant rate. However, we then replay the motion, putting a dot at where the car is at specific intervals, and we create what we refer to as a motion diagram. So each one of these dots represents the position of the car, and in between the dots, time had to go by. There was some change in time between dot 1 and dot 2 and dot 2 and dot 3 and so on. And what we can see is that the displacement between the two dots is constant for the interval of time. 2 seconds went by between the first and second dot. There was 2 seconds between each dot thereafter. Motion diagrams in general are drawn at a constant rate of time so that it's relatively straightforward when we're trying to describe the motion. We can say a couple of different things. One is the change in position relative to time is constant. The velocity is that change in position in terms of time. So we could say the velocity is constant. We can also note that since the first dot was furthest to the left and the last dot was furthest to the right, this is moving from the left to the right side of the screen. If we are thinking about a normal Cartesian coordinate system where the x-axis would be horizontal and the negative side would be to the left side and the positive side would be to the right side, and we make this first dot the origin on that coordinate system, then this car is moving in the positive x direction at a constant velocity. We can show the change in position, the displacement, or the velocity using a vector. If you're unfamiliar with coordinate systems and vectors, you might refer to the AP1 video lessons on those topics. It would be good to review those videos before continuing on without understanding those basic concepts. These vectors are not labeled. This could be the displacement vector, where each of those represents the change of position, or this could be the velocity vector, where each of those represents the velocity because it has a constant change in position and a constant velocity. However, they wouldn't necessarily have to have equal magnitudes. One could be longer, one could be shorter. In fact, without a scale, we have no idea what the change in position is relative to time, or what the velocity is with respect to time. It would be unlikely that the velocity and the displacement vector would have an equal magnitude. It's likely one would be longer or shorter than the other. We've already seen that the velocity is the derivative of position with respect to time, or it's the displacement with respect to time. But it's also related to acceleration. We haven't defined acceleration yet, but just a little foreshadowing. Turns out your change in velocity is the integral of acceleration with respect to time. If you have an acceleration function in terms of time, you can integrate it between the initial time and the final time, and that integration will give you the change in velocity over that time period. Remember that when we have a change in something, whether it's a change in position, a change in time, or a change in velocity, we always subtract the initial from the final. Describe the average velocity. That's a constant velocity that would have the same change in position over the same amount of time. In the last slide, we saw a car traveling at a constant velocity. So the constant velocity is the average velocity because it is not increasing or decreasing. We will see instances, and in fact, very soon we're going to see an example of a car speeding up or slowing down, where it's changing its velocity. And when you have a change in velocity, then we could determine the average velocity. When we're describing the average velocity, the easy way to do that is to get the total change in position over the total time. So final position minus initial position divided by the time it took to move between the two. There is another instance, which is we can take the final velocity, add to it the initial velocity, and divide it by 2. However, you have to be careful. That last function, that final velocity plus initial velocity divided by 2, is only true when you have a constant acceleration. There will be a few instances in this course where we will look at whether the acceleration is constant or not, and that can actually inform the way we might go about describing or analyzing the motion as it's taking place in the universe. We want to be able to describe the acceleration of an object, just like we want to be able to describe the time it takes to change position, the change of position in terms of the initial position and the final position, and the velocity as it travels from the initial position to the final position. The acceleration describes whether or not the velocity is increasing in magnitude or decreasing in magnitude. An object getting faster or slower is actually accelerating in the same direction as motion or in the opposite direction of motion. Acceleration tends to be confused for velocity by students. A lot of times students will think that when they're traveling really fast, they're feeling a fast acceleration, but they're not. If you're traveling really fast, you're feeling a high velocity. A lot of students will think when you slam on the brakes, you're feeling a low velocity, but you're not. When you slam on the brakes, you're feeling a large acceleration. In general, it's much easier for us to sense accelerations than it is for us to sense velocities. When you're in an airplane traveling at 500 or 600 miles per hour, you don't feel like you're traveling very fast because you don't have any reference to how fast you're going. However, when you take off in the airplane and you're only going from 0 to about 100 miles per hour, you feel a lot of acceleration. And while you climb in altitude, you feel a lot of acceleration. And in those instances, you would think you might be going faster than you are when you're cruising, but you're actually going much, much slower. The acceleration is a change in velocity with respect to time. The derivative of your velocity with respect to time is your acceleration. Since your velocity is the derivative of your position with respect to time, the acceleration is actually the second derivative of your position. So if we take the first derivative of your position function, we get velocity. If we take the second derivative of your position function, we get acceleration. Or what we're really doing is taking the derivative of your velocity function, which is also acceleration. A constant acceleration is an acceleration that does not increase or decrease, or there is no jerk. Jerk is your change in acceleration. A constant acceleration would get you from your initial velocity to that same final velocity in the same amount of time. Just like we described your average velocity, we can also describe your average acceleration by finding this change in velocity over time. So your final velocity minus your initial velocity divided by time is your average acceleration. If your acceleration is constant, then your average acceleration is equal to your acceleration at every instant in time. If there's a jerk present, so your acceleration is not constant, then your average acceleration would be a constant acceleration that would replicate or give you the same motion. One of the examples that this might come up in is if we're in a car and we're accelerating, each gear it goes through in the transmission has a different acceleration. However, if we want to describe the acceleration from 0 to 100 miles per hour, instead of doing the acceleration for each individual gear, we might do the average acceleration for all of the gears to be able to get a constant acceleration that would get that car from 0 to 100 miles per hour over the same time interval. Here we see a car this car just appeared. This car didn't drive in from the left side of the screen. Its initial velocity is 0. Again, if we just start looking at it, we might not have that information. If we start observing something right away, it's dangerous to assume that it started from 0 or that it didn't start from 0 without knowing one way or the other. In each of these animations, I've told you additional information to let you know what the situation is. When you're working problems, make sure you're cautious about whether or not you assume the initial velocity is 0 unless it tells you something like you start from rest, or it tells you that the initial velocity or speed is 0. You need some information about what it is before you start observing it if you're going to assume you know what's happening the instant you start observing it. Once that first initial time goes by, then our observation tells us whether it's moving or not moving. However, that first instant in time, the very T-naught, that 0 time, It's very dangerous to jump to assumptions. Let's unpause time and see what this car does. So we notice it accelerates to the right side of the screen. If we go back and get our position points or our motion diagram, where we have a dot that represents the car at equal intervals of time, when we look at the position diagram, we notice that the displacement is increasing. During each time increment that follows the one before it, the displacement of the car is larger. That means the change in position over that same increment of time is increasing. That means our velocity is increasing. So our vehicle, in terms of position, is moving from left to right across the screen. Again, using the Cartesian coordinate system, it's moving in the positive x direction. And as it's moving in the positive x direction, it's going faster. So the velocity, which is in the positive x direction, is also increasing. When we draw our displacement or velocity vectors, we should notice that as they go from left to right, they have an increase in the magnitude or increase in the length that's represented. The displacement or velocity vectors have an increase in magnitude as we go from left to right, that we're having a greater change in position for an equal amount of time. We're having a greater velocity as time goes on. We also notice that between our position points, we see another vector drawn down in between them, and that represents the acceleration. We're moving in the positive direction, and our velocity is increasing in the positive direction. So that means that you must be accelerating in the positive direction. If we were moving in the positive direction and our velocity was getting closer to zero, then we would actually be accelerating in the negative direction. Your acceleration can be in the same direction as position or velocity, or the opposite direction as position or velocity. And that determines whether or not the magnitude of the velocity is increasing or decreasing, whether or not the displacement for every increment of time is getting greater or being reduced. Your change in position or displacement vector and your velocity vector can never be in the opposite direction. Your change in position always has to be in the same direction as your velocity.